The ability of what? A capacitor to store charge is called what? Capacitance of a capacitor. Hope you are seeing it now. If you are being asked, differentiate between a capacitor and a capacitance. You say capacitor are what? Electronic device that helps to what? Store. That helps to store what? Charges. While capacitance is the ability. Are you seeing the difference now? The ability of what? A device. The ability of a device to what? To store charge or charges. To store electronic charges. Hope you are getting it. So that is just the two difference between your capacitor and your what? Capacitance. So let's proceed now. Mathematical formula for what? Capacitance is now given as C. C being your capacitance is given as the division of what? Your charge over what? Potential difference. That is, your charge here is your Q. Your potential difference here is measured in what? Volts. So if this charge, if you have to proceed, you can now say your charge mathematically, if you cross multiply, your charge can now be the product of your capacitor times your what? Potential difference, which is your V. So you are getting it now. So the unit of your what? Capacitance is measured in what? The unit of capacitance is measured in what? Farad. SI unit of what? Capacitance is what? Farad. Hope you are seeing it now. So that is just all about capacitance. Now let's proceed. There's what we call the parallel plate capacitor. We consider a simple capacitor in form of two metal plates. It's a material of permittivity E. You understand? A material of permittivity E, filling the space between them. Now, if the area of the plate is A and the distance between them is D, let one plate be charged as negative and the other as well positive. So from there, you can deduce that E being, you get it now. So this is your E naught. Now, if you have to proceed, you'll be able to now have your capacitor to give you as what? Your E naught. ER all over, multiplied by your A all over what? Your D. This is the capacitance of what? A parallel plate. Hope you are getting it now. So this particular value is actually for what? Electric field. Now electric field can be given as well your rho over what? Your epsilon. That is something like this. Your E naught. Now this particular formula is not actually being given. But when it comes to capacitance of a parallel plate, it's being given as E naught ER A over D, where your E naught is your permittivity of free space. Now this is your relative permittivity. See, permittivity of free space, while your ER is your relative permittivity. So these are the actual meaning of your what? E naught ER and your A. Where your A is your what? Your cross-sectional. Your A here is a cross-sectional area. So that as you can now, your D is your distance between the what? The charges. Let's proceed. Now we also spoke about the parallel plate of a capacitor, where the capacitance of a parallel plate is given as E naught ER E over what? Your D, where this is your what? Normal permittivity. Now this is what we call relative permittivity. So that has been dealt with the other time. Now, where we also believe that your relative permittivity is always given as 1. Now let's go to the arrangement of your what? Capacitor. You understand? In a circuit. The major arrangement of a capacitor in a circuit. Now if you recall, in our current electricity, in our subsequent lessons, we spoke about the arrangement of our resistors in a circuit, where we talk about resistance of a resistor or resistance in a particular circuit. Now, then we spoke about resistance being in series. This is a series connection where you have your first resistor, second resistor, and third resistor. Now the total resistance here now we said the total resistance will give you your R1 plus R2 plus what? R3. Why? We established the fact that then that this type of connection of your what? Resistors, they always be in what? They are in series. So for you to actually bring out the mathematical calculation, you are being given, you are going to have it like this. But when you have them in what? In parallel, that's series connection. This is your parallel connection. And when you have your resistors in what? Parallel, that is something like this. You have the 1 over total resistance will give you 1 over R1 plus 1 over R2 plus 1 over R3. So from here now, we can now see what? Our total resistance will give you R1, R2, R3 over R1 plus R2 plus R3. This is the what? Total resistance of a circuit which has resistance arrangement in what? Parallel. While this is the total resistance of a circuit which has resistance, a lot of resistors in what? Series. So the first case, we're looking at 2 or more capacitors in, you understand? In parallel arrangement. Parallel arrangement of 2 or more capacitors in a circuit. What am I saying? Look at something like this. You have your charge. This is Q1, C1. Now you now have something like this. This will be your Q2, C2. Now this is a circuit. You come down, you understand? For us to have a potential difference at this region. Now with this type of settings, you realize that this is a circuit which has 2 capacitors. Now of course, wherever capacitors exist, there will be charge. Now in this first case, now this is your what? C1. This is your first capacitor. You understand? Now automatically it's going to have a what? A Q1 charge. Here too, this is your Q2. Automatically it will have a Q2 charge. But in the circuit which has a parallel arrangement of capacitors, this is what happens. You definitely now have your total. You have to calculate your total what? Capacitance. So your total capacitance in this case now, because they are in parallel, will give you your C1 plus C2. What do I mean? They are just like the arrangement. Let's put it this way: arrangement of capacitance, or let me say formulas of arrangement of capacitance, or let's say capacitor, is inversely, let's put it this way, inversely proportional to what? To the formula of arrangement. I'm definitely writing this so that you'll be able to get it straight up. Is inversely proportional to the formula of arrangement of what? Resistors. What do I mean? If what we have here is, let's say for instance, R1, R2, definitely it won't be this. It will just be 1 over RT. You get R total, R1 over R2. You understand? So definitely you have to get it straight in your head that if you have a circuit now that has 2 or more capacitors or capacitors, now for you to calculate the total capacitors that exist, you understand, in this circuit, you just write out the formula in a straight word here. Why? Because at this region, you understand, we have the same passage of what? Potential volts. You understand? When you get to this place, there is what? Same movement of what? Potential difference across this circle. So automatically, your what? Your total capacitance will just be addition of C1 plus C2. You get? Now, if you now have them, this particular formula is majorly used when your what? Capacitance is what? Is in parallel. You get? Now, when the capacitance is now what? In series, you have your what? C1, Q1 equals C2, Q2. Now, if you have something like this with same what? Potential difference, you realize that the what? The total capacitance will now be CT. Will now be 1 over your total capacitance, then 1 over C1 plus 1 over C2. This is the formula for series connection. Why we have this formula for what? For parallel connection, which is just the total inverse of what? Parallel connection of your resistor and what? Series connection of your what? resistor. So that's just what I mean. So when you have your capacitors being arranged in parallel, you use this straightforward formula. Now when you have them arranged in series, you use the what? The inverse formula. Now, at this junction now, we'll look at how those formulas are actually being derived. First of all, you say, my Q gives me CV, which is capacitance times what? Potential difference. Now, you now tell me that your Q1 will definitely equal to what? C1V. Why? Why is V constant? V is constant because the potential difference that leaves the source here, the EMF source here, is being distributed equally to the two charges. That's why your V is constant. So if you have your Q1 equals C1V, now if you now have Q1 equals to Q total equals to Q1 plus what? Q2. Meaning that the total charge here at this region will be equal to addition of your charge of Q1 here and your what? Q2 here. So what do? You substitute the value of this one. You know your Q is CV, so you just substitute them in. You now have CV. You know definitely this is total equals to this is QT. It's going to be C total equal V equals to CV1 plus what? CV2. Potential difference. So you just cancel out this potential difference here. Automatically, you're going to have your C total to equal to C1 plus C2. That is how the formula for what? For parallel connection of your capacitor is being derived as well. C total equals to C1 plus C2. Now let's go to the next one. If you now have a series connection of this